Hello! Hello, everyone. Can folks hear me okay? Okay, all right. Thank you so much for spending your Friday night, even a cloudy one, with us. We're very excited to have you here. Can I see a show of hands if this is your first time at one of our events? Wow, incredible. We're so excited to have you. My name is Amanda. I'm a lecturer in the department, and I'm also the outreach coordinator. I host these talks. Today I'm also going to be giving the talk, so it's double Amanda today. Woo, all right. I'm thrilled there are no boos. It would have been a really long night otherwise. So how this works is we're going to check in with our prior knowledge first. We're going to do trivia. I'll talk about our schedule for the rest of the summer. Then I'll give my talk, and at the end we'll have Q&A and a raffle. So we have 5 questions for trivia. I'll let you all know how we do this. I'll show a question. You'll have time to think about it. Collaboration is strongly encouraged. Our collective knowledge is always more than our own knowledge. Then after I think conversation has started to die down, I'll say 3, 2, 1, vote. Everyone will show me 1 for A, 2 for B, 3 for C, or 4 for D based on your thoughts, and then I'll reveal the answer. So I promise I will explain what spectroscopy is in my talk. These are supposed to be fun kind of teaser questions, so don't feel worried if you don't know them. Question number 1. What the heck is this? Lots of good deliberation. I always feel bad cutting you off, but let's go ahead and vote. 3, 2, 1, vote. Okay, I see 2s. I see 3s. Do I have a 1? Do I have a 4? Oh, I do have a 1, but maybe no 4s. Maybe I'm missing it. It is light shining through a diffraction grating. So as I will explain in my talk, spectroscopy is when we spread out light, and we need a tool to spread out the light. You might be more familiar with a prism, but a diffraction grating does the same thing. It gives us these rainbows. All right, question number 2. What color of light does the sun emit the most of? Okay, let's see your answers. 3, 2, 1, vote. I see, oh yes, 5 for E. I see some 5s, I see some 1s, I see 3s, I see 4s. Do I see a 2? I don't think so. And the answer is blue-green. So we've been drawing the sun yellow since we were in preschool. Does that mean we are all wrong? No, it does appear yellow to us, even though you should never look at the sun, right? But the sun emits at all visible lights, and when you add that light together, it becomes white. So our sun, with our eyes, looks kind of white, kind of yellow, and if it looks more yellow, that's because blue light is scattered in our atmosphere. That's why our sky is blue, the blue light is scattered, so what's left is a more yellow color. So now you can tell your children you've got to draw a green-blue sun. Question number 3. Which is not a real element from the periodic table of elements? Okay, 3, 2, 1, vote. I see some 2s, I see some 3s, I see 4s. I see a 1. Well, we love to trick you. There are 2 false elements here. They might have been in the World Cup final, but they are not on the periodic table of elements. Okay, beware, this is our most physicsy question. Spectroscopy is the result of particles having specific energy levels in elements. What causes this? Okay, 3, 2, 1, vote. I see 3s, I see 5s, I see 1s, I see 1s and 5s. People aren't getting tricked twice. All right, but the answer here is just 1, quantum mechanics. I actually took quantum mechanics at the other end of this hallway, and one time I got a 20% on an exam. And I say that not to brag, but just a reminder for the students, even if you fail an exam, you still belong in a field. That won't stop you from getting a PhD. Okay, and our most serious question of the night. JWST is the largest space telescope, and it can do spectroscopy, but just how big is it? I hear a lot of careful deliberation, but I don't see anybody doing math on pen and paper. Okay, let's vote. 3, 2, 1, vote. I see 2s, I see 5s, I see 3s, 4s, and a 1. All right, well, it is salamanders. So astronomers use funky units sometimes. We don't use any of these, but at the end of the day, a unit is whatever you want it to be. All right, a round of applause to everyone. You all did great. Okay, for especially all of the new folks, the best way to find out about our events is to join our mailing list. That's where we send the registration forms and the schedule. We have one more talk this summer. It's August 28th in this room at 8 p.m. And then we will announce our fall schedule at the end of August once Columbia lets us book this classroom. But for now, we're going to learn about stars and their light. So just to make sure we're on the same page, I'm going to define two celestial objects that I'll be talking about, stars and galaxies. Stars are these huge, giant balls of gas and plasma. They give off light, energy, heat, whatever you want to call it. This is a picture of our sun, the most well-known star. And then next to it is my second favorite galaxy, the Andromeda Galaxy. Galaxies are collections of stars and some other stuff I don't care about. So these objects are so far away, not our sun, but any other star and any other galaxy, that we can never, ever get to them. We can't get in a spaceship or send a probe and go out to collect samples or to do experiments. So the only way we can know about these objects is to study their light. And there are two main techniques for studying light. Oh, and that's because space is really big. Space is really big, so we can't go out there. So the first technique to study light is just to take a picture of it. And we get these beautiful images of galaxies, of nebula, of our own planets in our solar system. These images are really important for understanding the structure of objects and also for inspiring humans thinking about space and being able to actually see these things that our eyes otherwise cannot see. So while these are beautiful images, we can learn more about the light if instead of taking a photo, we spread it out. And so when we spread out the light, this technique is called spectroscopy. That's what the talk will be focused on. When you spread out the light, you get a spectrum. This is the rainbow that we see. And what we see actually is that our eyes can only see the rainbow, visible light, but there's so much more light out there in the universe. So even if you're a sighted person, we are blind to most of the universe. So we need to build detectors that can spread out the light of all kinds of light across the electromagnetic spectrum. So even though there's lots of different kinds of light, in this talk I'm going to be using a rainbow to represent a spectrum, since that's what our visible eye, since that's what our eyes can see. Okay, so we have a star and we shine its light through a prism, then we're going to get a rainbow. That's what we expect. But in reality, the star's light has to go through its own atmosphere. So you maybe don't think about stars having atmospheres, but they do. And the atmosphere blocks some of the light. So instead of getting a full rainbow, we get something that looks like this. And it has these gaps in the spectrum. So these bands, these black bands where there is little or no light. And that maybe sounds annoying. You'd probably think we want all of the light. But actually, it's a delightful phenomenon in the universe because these gaps tell us way more about the object than the rest of the light does. And that's because it turns out that these gaps are correlated with the stuff that's in the object. Specifically, the elements or the molecules that are in, let's say, the star. So we can take an element, any one from the periodic table of elements, and burn it in a lab and look at the light that it emits, and we see that it has a pattern that lines up to these black bands. So if we see the first pattern in a star's spectrum, we know sodium is in the star. So then all we have to do is look at the patterns in a star's spectrum, and we know what kinds of elements or molecules are in that star. It's of course more complicated than just looking at one pattern at a time, because stars have lots of stuff in them. So if we have two hypothetical elements, A and B, they're not real elements. If we looked at the star's spectrum, we would see the patterns added together. So it becomes a little bit more complicated pulling out these patterns, but luckily we have computer programming that is faster and better at doing this than humans. These are pictures of spectra. In reality, astronomers don't analyze the pictures, they analyze a graph of the spectrum. So we can turn a picture into a graph. So on the top here, I'm showing a picture of a spectrum, and on the bottom, I'm showing the corresponding graph, where on the x-axis, we have the kind of light, or the wavelength of light, and on the y-axis, we have the amount of that kind of light. And if you line up the absorption lines and the graph, you'll see that there's still some light at these dark bands. It's not that there's actually no light there, it's just that there's missing light. And we can study these absorption lines, where they are, and how big they are, and that tells us what kind of elements are in the star and how much of them there are. In reality, astronomers tend to not add pretty rainbows to their spectra. Instead, we have black squiggly lines. So we're definitely not getting the beautiful images I showed at the beginning, but remember, there's so much information encoded into these squiggly lines. You maybe can't tell from looking at these, but these are stars in the Andromeda galaxy that were taken with the Keck telescope. So we'll talk much more about the Keck telescope. Okay, I hope you all are astounded, amazed that we can figure out what is in a star that is trillions of miles away just by looking at its light. So hopefully that would be enough, but there's also more that we can tell from a star's spectrum. So not only do we look at the patterns, we look to see if they're where we expect them to be. So remember, we can do experiments in a lab, so we know exactly where these patterns should be. And when we look at stars, we see the patterns, but they're a little to the left or a little to the right. They've shifted. And that shift means the star is moving. Everything moves in space. It makes it really hard to study space, so that's not a big surprise. But we can actually calculate how fast the star is moving and know about its direction. So this maybe feels very foreign, but you can counter this in your daily lives. So if you are a hearing person and you're standing still and a fire truck with its siren on is coming towards you, what do you hear, or what happens to the sounds? You can just shout it out. It's louder. What else? Higher pitch, okay? So as it approaches you, it both gets louder and the pitch increases. What about when it goes away from you? Lower pitch. Now, do you think someone in the fire truck is like, I'm going to pull a prank on this person? And they're changing the pitch of the noise for you personally? Probably not. Yeah, I agree. And what actually happens is the sound waves in front of the truck get compressed because they're being run into each other as the truck continues, so the pitch increases. And when they're behind the truck, they get spread out. They're being left behind as the truck moves in the opposite direction, so the pitch decreases. Light is also a wave. It's a different kind of wave than sound, but it also has a pitch or a frequency. We call it frequency for light. And so if we have our lab absorption line spectrum, if we see it in a star that's shifted, we know it's moving because the light waves were either smushed together a little bit or stretched out. So the black bands on the top don't correspond perfectly with where the black bands on the bottom are. The pattern is still the same. The ones in the stars have just been shifted a little bit towards the red. And that tells me the star is moving away from us because red light is a longer wavelength. So we know stars are moving. We can see this in absorption lines, but we can also calculate how fast they're moving. And so I'm going to put you all to work, and we're going to do that right now. So what I'm going to show you is called a Jupyter notebook. This is a place where you can put computer programming code. I'm using Python. That's the favorite language of astronomers. We use computer programming code to process our data. It's too much to do it by hand. It's too imprecise. So we use computers. You don't need to know Python for this demonstration. I'm going to have it graph a star's light. This star is another one from the Andromeda galaxy that was observed with the Keck telescope. It's a red squiggly line, so different color, but that doesn't have any meaning. Do you all see absorption lines in this? Yes. All right, so we can learn about the star's light, but we can't learn about the star's light if we don't have anything to compare it to. So I've mentioned a couple times we look at lab experiments to learn about where absorption lines should be. And so we can use that and a computer simulation to model stars. So make kind of fake stars on our computer that we predict represent real stars. So now on this graph, I'm going to add a model of a star. The black squiggly line is our model, our template. The red is the real data. Is the model a perfect representation of our star? No, but that's okay. There are hundreds of billions of stars out there. It would be honestly weird if we perfectly predicted one at random. Is it a horrible representation of our star? No. So this is where astronomers oftentimes have to shrug and be happy with good enough. This is good enough. And we are not engineers, so we can get away with that. No building buckles when we say good enough. All right, so even in the places where it's not great, we still in this area seem that it's sloping up in both. This area seems to be the biggest disagreement, so we will just zoom in on another part where there's better agreement. So this is still the same two lines. I've just zoomed in so you can see the absorption lines better. I've specifically zoomed in on what's called the calcium triplets. So we have one absorption line, two absorption lines, three absorption lines. That's a signature of calcium. So we know there's calcium in this star in Andromeda. Do the black dips and the red dips line up perfectly? No. No, what does that mean? The star is moving, it's shifted. Okay, so the work that you all are gonna do is you're gonna tell me how much it's shifted. So we wanna move this black dip so that it lines up with this red dip. So first, do we need to move it to the left or to the right? To the left, okay. This mark, this size interval represents 50. So do we need to move it bigger or less than 50? Less. All right, and this is where it's very fun. We get to just try stuff out and see what happens. So it's going to be negative because we're moving to the left. So someone give me a number less than 50. 10. Okay, I heard 10 the loudest. So the black line's going to move. All right, we did a little bit too much. We overshot it. So we need to do smaller than 10. All right, I heard 4 first. Oh, it is good enough. Okay, so I've been saying 4, but we care about units. They contextualize numbers for us. This is 4 times 10 to the negative 10 meters. Is that small or big? It's really small. It's so much smaller than our eyes can see. It's smaller than a width of hair. You would need a very good microscope to see this. This is why we need really state-of-the-art technology to be able to detect this change. Our eyes would never be able to see this. So 4 times 10 to the negative 10 meters, that's how much we had to shift this. Let's see how fast or slow this corresponds to. So I'm not going to make you all do the math. So you can pick your unit. I grew up in the US, so I unfortunately learned miles per hour. So I'm going to look at this number. That's over 300,000 miles per hour. Is that fast or slow? It's very fast. It is faster than we can go on Earth. It is the speed that our fastest spacecrafts go. So stars are moving incredibly, incredibly fast. And the wild thing is, they're so far away that we don't even detect this movement. So even though it's traveling more than 300,000 miles per hour, if you go out and look at Andromeda today, and then in 1,000 years, this star is basically going to be in the same spot because the galaxy is so far away. Another thing we learned about this number is that the star is moving towards us and not away from us. And this is the technique that astronomers use to discover that it's not just some stars in Andromeda, it's the entire galaxy that is moving towards the Milky Way. All right, round of applause. You all did data analysis. So I hope you are thoroughly convinced that spectroscopy is worth doing. We learn about what is in the star, how fast it's moving, and if it's moving towards or away from us. So let's do a case study. Let's think about how we would observe. And we'll do this with my favorite galaxy, the Triangulum galaxy. It's a spiral galaxy, like our own Milky Way, but it's 100 times less massive, so it's fairly small, and it's 3 million light years away. So it takes light leaving the galaxy 3 million years to get to us. So I can tell you what the galaxy was like 3 million years ago. I can't tell you what it's like today. It also has 40 billion stars in it. That's less than our own galaxy, but it's still a sizable amount. And when we do spectroscopy, we need to isolate every single star. If the light from 2 stars mix together, then those absorption lines are going to mix together, and our analysis will not be correct. So, thinking we have 40 billion stars, we need to isolate all of them. Do you think we can do this with all the stars in Triangulum? A room full of pessimists. But your intuition is correct. But let's give some reasons behind that. So I'm going to have us focus for a moment on a sense of scale and ask you, how much is a billion? Well, obviously it's a billion. But what does that mean? We use the word billion all the time. I say my office is 1 billion degrees. I have 1 billion things to do. There are 8 billion people on the planet. So maybe it's not that much. So let's try to recontextualize this by thinking about, can you count to 1 billion?
Probably not.
I hear a little more discussion than the flat-out no's we heard before. I'll let you think about it for like 10 seconds. Okay, this time when I say 3, 2, 1, just say yes or no. We'll all say it at the same time. 3, 2, 1. Go! All right, a mix. So I have no doubt that all of you know the numbers between 1 and 1 billion. It actually becomes a matter of time. So if we're counting to 1 billion, how many numbers do we have to count? 1 billion. We're going to estimate and say it takes me 5 seconds per number. Remember, we're good enough astronomers here. So at the beginning, I can say the numbers really fast, right? 1, 2, 3, 4, 5, 6. But when I get to 562,387,924, that takes me longer, right? So on average, 5 seconds. There are way more big numbers than there are small numbers. So if we estimate it takes 5 seconds per number, that would be 5 billion seconds. Well, that means nothing to me. Is that 2 days? Is that a year? We have to do unit conversion, and it turns out it's 158 years. I also did not take into account the fact you have to sleep and eat and drink water and maybe have a social life. So no, you cannot count to 1 billion. The world record for counting was done in 2007. Oops, too far. 2007, by someone who counted to 1 million. He spent 16 hours a day, which is longer than I have ever worked in a day, and it took him 89 days. So also I hope that provides a sense of scale between 1 million and 1 billion. 89 days versus 158 years, less than a year over human lifespan. So 1 million plus 1 billion is still 1 billion. All right, so you all correctly said we cannot do this with triangulum, and we also have to take into account realistic observing conditions. We need triangulum to be up. We need it to be nighttime. We need the weather to be good. We have to look at each star for about 2 hours. So if you did that, it would take you 220,000 years to observe all of the stars in triangulum. I plan to retire sometime, so we can't do this in triangulum. So if we can't do this in triangulum, we have to pick stars. The goal of my science for my PhD was to get an idea of what's happening overall in triangulum. So for that, do you all think I want to pick boring stars or interesting stars? I heard some interesting, I heard some boring. Both are good choices. For my goal of just to know what's happening overall, I want to pick the boring ones. Just ones that represent the population that aren't doing anything outstanding. Okay, so I have my plan. I know I can't look at all the stars. I need to start planning my observation then. My telescope that I use, the Keck telescope, has a really narrow field of view. So field of view is what the camera sees. It can't see all of triangulum at once. It can only see this narrow rectangle. And inside that rectangle, there are stars I want to observe, and there are far more stars I do not want to observe. So that would be like saying, if I stood here and I want to pull out my phone and take a picture of the audience, but I only want to capture people who have glasses on. How do I do that? Let's hear some ideas. No idea is a bad idea. I zoom in. Okay, I could zoom in, but that's going to take me even longer in this case because I want to observe as many stars as I can at once, so that's true, but let's keep trying. I heard another one. Sorry? Object arrays? Oh man, would love that. But I would still have to first image all the stars and then click on all the ones I didn't want. So also possible, but not our most efficient idea.
Use Photoshop and take out the stars you don't want to do.
Yeah, I wish I could. Too many stars. Shine a light at it, so maybe the light could block some stars. Unfortunately, any light I shine is going to take 3 million years to get there. All right, I'll give you a hint. What if, along with my phone, I had a piece of aluminum foil and a thumbtack? Okay, so what if I put the aluminum foil over my phone camera and I poked holes that corresponded to everyone that had glasses on? So my phone blocked out everything except where people were wearing glasses. So that's actually what we do. It's called, in this case, a slit mask. So it's literally a piece of metal that we carve slits into, and each slit will line up with a star that I chose to observe. The slits look like lines, but they're actually 2D boxes, so little rectangles. And the nice thing about the slits too is they spread out the light vertically, so I can get my spectrum of a star. It means none of the slits can overlap, so there's a limit to how many of them I can put on the mask, but it's kind of like two birds with one stone. So I designed this on a program called D-Simulator. D-Simulator is so old, there are 2 computers in the world that run it, so fingers crossed those computers never die. And it helps us to optimize the stars that we give it. It picks based on the priorities we've assigned the stars to put as many on our masks as possible. Then when we're satisfied with it, it creates this kind of schematic, a plan, and we send that straight to the observatory that will drill the slits into a piece of metal for us. This is a zoom in of a slit mask, so if you ignore all the fingerprints on it, you can see these slits. They're different sizes, but none of them overlap. They get as close as possible. And you also see a box. That's an alignment box. That box we want to line up with a really bright star, and we have 6 of them on each mask, so we can know if we need to turn or rotate the mask a little bit so that all the stars actually line up with the slits. This is the most important thing, because if you're off by a little bit, you're not going to get any good lights. So you can imagine how scared I was the first time I did this. So after you design your slit masks, you then need hardware. And so what we do is we use a telescope. Telescopes capture the lights from a star or a planet or a galaxy. And then we send it through an instrument, a spectrograph, which spreads out the light like a prism. A camera then captures the lights, so even the spectra can be captured by CCDs, just like your phone uses. And then that's sent to a computer where we store the data and then we can analyze it. For this specific talk, I'm going to discuss the Keck telescope and the DEIMO spectrograph. There are 2 telescopes, Keck 1 and Keck 2. The telescopes are identical, but they have different instruments. The center image is what Keck 2 looks like. And on the right, that's me with DEIMOS. I know I am small, but DEIMOS is large. And before I continue, I just want to highlight that this telescope is on Mauna Kea, and Mauna Kea has always played and continues to play a very significant cultural role to the indigenous Hawaiian community, so we are very fortunate to be able to collect data from the summit. The Keck telescope is big. It is 10 meters across. That's 30 feet. And so let's do a quick estimate. Would it fit in this room? I think so, but it would take up the whole room. Nobody else would be able to sit here. It might be a tight squeeze. Because it's so big, it also weighs a lot. It weighs 300 tons. But it has to move incredibly precisely. It cannot vibrate or that will mess up our instruments, and it has to move quickly. So how they've engineered this is it's floating on pressurized oil. So something that's 300 tons is floating. It's so big we can't have one single piece of glass make the mirror. It would be too heavy, it would likely get warped, and if it broke, you'd be really in trouble. So instead of having one 30-foot piece of glass, they have 36 hexagons that they piece together to make one continuous surface. These hexagons are much easier to replace and to fix. The right image is the back of one of these hexagons with one of the engineer's hands for scale. And on the back there are all of these little pistons that poke the mirror or poke the hexagon until it's the exact shape we need, so you have a continuous, slightly curved surface. Keck requires also a lot of data storage and a lot of power. There are whole closets full of circuit boards and hard drives. And this is just to emphasize that astronomy needs so much more expertise than astronomers in order to function. Keck is on the summit of Mauna Kea. It is the tallest mountain on Earth if you count from the sea floor. It beats Everest if you start down in the ocean. And it's so high up that you can get altitude sickness fairly quickly. There are other telescopes on Mauna Kea that have more relaxed rules. I think something must have happened at Keck once, because they say, astronomers, if you are staying up all night and have altitude sickness, you are bad drivers, so you cannot come up and observe from the summit. So instead, we are on Zoom with the telescope operators in an old cowboy town called Waimea on the same island, the big island of Hawaii. From Keck headquarters, you can see the domes on top of Mauna Kea. You can check to see if there's any snow. Mauna Kea is so high that often there are blizzards, and therefore we can't observe. Here's another image I really like. It looks like the domes are floating in the sky. Okay, so you've planned your observation, you've made your slit mask, you've gone all the way to Hawaii, you then have to observe. So your day starts around 4 p.m., where you do what are called calibrations. So we want to make sure we understand our camera, if there are any biases or systematics. But you're not allowed to touch the telescopes until the engineers are done with their daily maintenance. So we go to this website to see if they're ready or not. It's also fun because we can kind of be nosy with Keck 1 and Keck 2. So what I'm showing, K1 is Keck 1, K2 is Keck 2. It tells us the instruments that are on there, high-res and OSIRIS for Keck 1, and MOSFIRE, and NIRSPEC and NIRCam 2 on Keck 2. None of them are ready, so astronomers can't start their day. We can spy even more. We can see the names of the astronomers who are observing. SA's support astronomer. They're the ones who actually know how the instrument works, and their job is to babysit you and make sure you don't break it. And then the OA is the telescope operator, the person at the summit who is actually moving the telescope. Okay, so whenever you get the instruments released, you take calibration images. That takes between an hour and an hour and a half. Then you run off and you get dinner and something to keep you up all night, so some kind of caffeine. I like a fruity black tea. And then you observe. There are 3 possible time slots for observing. You can observe the full night, so whenever it's dark, sunset to sunrise. My favorite, because I prefer sleep than astronomy, is the first half of night, where you start at sunset and then you go to bed at a very reasonable midnight. Everyone's least favorite shift is the second half night, where you start at midnight and you go until sunrise. And I can tell you that based on the instruments that were on the webpage, since there are 2 on each telescope, the night has been divided into 2. So some poor astronomer tonight has to stay up until 6 a.m. And then you go to sleep, and you make sure you are up and ready by 4 p.m. the next day to start observing again. I told you don't have control of the telescope, but you do have control of the instrument. You're not physically there, but you get to press the buttons that do things to the instruments. So this is for Deimos, the Deimos spectrograph. Remember, this is the instrument that stretches out our light like a prism. This is what its GUI looks like. I can change the slit mask and a whole bunch of other things. What I'm now going to show is a recording, is a recording of me and who was my PhD advisor at the time, Professor Raja Guhathakurta at UC Santa Cruz, as we are observing on Keck. So this is us observing for real. I'm going to spoil the whole video and then show it to you. You're going to hear his voice explaining what's happening. You're going to hear the computer say, exposure complete. That means it's done collecting data from the stars that we're looking at. You'll hear me say I'm going to change the slit mask. You'll hear the telescope operator say he's moving the telescope to our next target. You'll hear readout complete. That means the computer has flushed the camera. The data is no longer on the camera, and it's on our computer. And then you'll hear Raja say that we have new data.
Good. In the meantime, it is almost finished the exposure, so you can see 1043, 1044. When it hits 1050, you'll hear a voice saying exposure complete.
Exposure complete.
Okay, and now,
Change the mask of the image.
way up. So what Amanda's going to do is change the mask to a different metal plate.
Yep, I'm slowing now.
Thank you. So this thing that went way over here in this part, it's because Amanda's requested a change in the instrument configuration. A different metal plate is being moved in where the old one was, a different mask. And we're also changing the tint of the grating to go from first order to zeroth order. The object name is also something that we will change. Instead of PTH1, it will be PTST2. And that's something that will reflect our site.
CTD readout complete.
You can see that it updated, I don't know if you can see that it updated the image of the spectrum.
All right, so that is what observing is like. Raja is famous for inviting random people he met on the plane to Hawaii to come observe with us. And so they're so excited to be there. They're using one of the biggest telescopes on Earth. They're really sleepy, but they're doing their best to stay up. We've looked at something, we've been taking data for 2 hours. They hear exposure complete, readout complete, and they're so excited. And then they see this and they go, oh. And we're like, okay, we get it. It's not the beautiful image that you were maybe expecting, but it tells us about what's in the stars and how fast they're moving, so I think it's more valuable, even as our black squiggly lines. If you are interested in that video, Raja, because he loves sharing observing with people, has started an organization called Shadow the Scientist. He figured if we're on Zoom with the telescope operator, why not let other people join the Zoom as well? So this has expanded. It's now on other telescopes, other fields of science, chemists using electron microscopes, ocean liners mapping the ocean. So these are not glamorous, these are not planned things, these are science happening. It's tedious, it's boring, but you get to see what doing science is like, and you get to talk with the scientists as they do their work. These sessions pop up kind of sporadically, so make sure you visit the website frequently, and it's totally free and open for all. Sometimes they are at gnarly times because of time zones. All right, and with that, thank you all so much for listening to me. I'm happy to take any questions. You can either raise your hand and ask, or you can submit your question online if you feel a little nervous. All right, first question in the back. A comment, okay. Go Spain. All right, question over here.
So when did they discover that it was light we could not see?
Yeah, when did they discover light that we could not see? That's a great question. I think the different kinds of light were discovered at different times. I'll tell you how, I don't know if this is how microwaves were discovered, but one fun fact about microwaves is that someone was experimenting with them, and then a chocolate bar he had melted, and he was like, what's up with this? And so that's how your microwave happened. So that doesn't answer your question. I'm pretty bad about this history of science, but it is a great question. At some point in probably the not too far past, humans didn't know about different kinds of light. Yes?
Is there much commonality between the contents of stars and you break them up into categories?
Yeah, is there a lot of commonality between the contents of stars, and do you break them up into categories? Yes and yes. Stars are mostly hydrogen, and then they're mostly helium, and then they could be some other stuff. based on where and when the star formed determines how much other stuff it has, also what evolutionary phase it's in. So looking at the kinds of stuff that's in stars and the amounts of them can give us an idea about when it formed, where it formed, and what evolutionary phase it is. Yeah. Question? Yes?
Do all stars have atmospheres?
Do all stars have atmospheres? Yes. And something weird about stars is that their atmosphere is significantly hotter than their surface, and we don't know why. Yes?
Are stars moving at the same speed?
Are stars moving at the same speed? It depends. So in a spiral galaxy, stars are rotating around the center of the galaxy, similar to how the planets orbit around the sun. So those stars, if they're the same distance from the center of the galaxy, they are moving about the same speed. But the stars that are closer are moving a different speed than the stars that are very far away. And that's because gravity holds them together. Yes?
Do suns also spin themselves? And I had a theoretical question in my head, like if in theory you could look at the light from each side of the sun, you could tell then how fast it's spinning, but is that feasible or no?
Yeah, so do stars rotate in addition to orbit, and does looking at light from their left or right side tell you anything? Stars do rotate. Our sun rotates fairly slowly, so most stars do, and how fast they rotate might tell us something about their age. Aging stars is really hard to do. Looking at the left and the right side of a star is more useful for if you're looking for planets. So to see if there's differences or if there's sunspots on the stars, that might show up there. Question? Yes?
Even though the telescope's pretty high on top,
Mm-hmm.
is the atmosphere still sort of impacted the absorption line?
Yeah, so even though Keck is really high in altitude, does it still impact our observations and the absorption lines we see? Yeah, one of the biggest absorption lines we see we call A band for the atmospheric band. So if astronomers were given evil, like super villain evil power for a day, they would for sure get rid of the atmosphere because it makes it much harder to see things. That's why we have telescopes in space. So even though it's so high up, it still has to go through some atmosphere. Okay, I'm going to take a couple online. What's the best season for looking at stars? Does the light change depending on the Earth's position? So the best season, I would say, is fall because the weather tends to be best. That's why we haven't observed yet, because it's been spring and summer. But it really depends on what you want to see. Like the Triangulum galaxy is not in the sky the entire year. So I couldn't in May say, oh, I want to go to Hawaii. Let me see if I can make it an observing trip to see Triangulum because it's not up. So it depends on what you want to see. Let's see. Doesn't the fact that stars are moving towards the Milky Way contradict with our understanding that the universe is expanding? So the universe is expanding, and Andromeda is moving closer to the Milky Way, and those things are consistent with each other. On small scales, gravity is stronger than the expansion. So things that are relatively nearby in our galactic neighborhood, they're going to continue to come towards each other, but things that are outside our galactic neighborhood are going to continue to go farther and farther away from us until we eventually can't see them anymore. Okay, I think we'll do last question. Yep.
I was wondering if you're doing a sort of Zoom call with the people holding the telescope, why do you have to be in Hawaii? Especially because, obviously, midnight to 6 a.m. would be 6 a.m. to midday here, so there's a lot of time to see from it.
Yeah, so if we're on Zoom, why do we have to be there? Well, historically, it was for security reasons. They wanted it to be a secure connection so the data was safe so no one could join on Zoom. But then the COVID-19 pandemic happened and it was no longer safe to travel, safe to be in the same places with others. And so they then did a lot of work to convert to what we call pajama mode, because if you're in your home, you can be in your pajamas. And so now, yes, you can be anywhere in the world and use Keck. lots of people like to be there. You get to talk in the same room as the support astronomers. You get to, after you're observing, go up to Keck and see the telescope if you want. So it's still nice to travel and be in person, but if you can't afford to travel, or your schedule doesn't allow it, or you're caring for folks, or you want the East Coast time, you certainly can do it from your home. Okay, with this, we're gonna do our raffle. Thank you all for your questions. So look at the back of your chair. There's a number and a letter there. Usually these numbers are used to put people in assigned seating for exams, but we use it for a much more fun cause. Okay, there are a lot of seats here, so I'm just gonna start saying I have a random number generator. If I say yours, scream really loudly because I only have 4 prizes, so don't let me overpromise. And you can come get your prize on your way out. Okay, P8, J15, H13. All right, H0, B10, D2, J4, J18, N9. All right, G8, H3, H11, G11. Oh my gosh, P11. All right, H18, D7, H4. All right, give it up to our winners. All right, thank you all so much for coming. I hope to see you in August. Maybe we'll have clear nights.